The next thing I'd like to discuss is the solution to homework 3, problem 9. And we have a cube on a wedge. They're all frictionless, and we want to figure out how fast the wedge is accelerating to the right. I have a coordinate system given in the problem, but I am going to do something a little funky here, make my math easier, and pick a emergency backup coordinate system for the cube. The reason I really want to do that is that the cube is constrained to accelerate up and down the wedge. It's not going to go flying off the wedge in the vertical direction. Therefore, I can get good equations of motion for the cube. In particular, I know that its acceleration in this y prime direction is going to be 0 because it sits on the wedge. And therefore, for the cube, I've got some forces on it. We're on Earth. There's some gravity. I got a weight, mc times g. I've got a contact force of the wedge on the cube. That's a normal force. And as I've drawn it, this angle here will be theta. And this angle here will be up and down the wedge. And therefore, we have that this angle here will be theta. Okay, now that allows me to project the weight into the plane of the wedge, or the surface of the wedge. Let's put that on hold for just a moment, finish off our free body diagramming. Got a wedge here, it's got a weight. It's got a normal force that pushes up, keeps it from falling through the table. And we have the equal and opposite force here for the wedge on the cube. We have the force of the cube on the wedge. And as I've drawn it, that angle there is theta. Now, the reason I'm going to take advantage of my coordinate system here, I'm going to say the sum of the forces in the y prime direction is going to be 0, and that is going to be equal to mc times the gravitational constant. Oh, sorry, this is negative because it's going opposite the direction I've drawn my y prime axis. Where were we? Oh yeah, we were cosigning away. So that component of this little right triangle is the cosine component. That's mcg cos theta. That exactly balances the contact force because otherwise it would accelerate. And that gives us a nice relationship. The reason why I do this is I want an expression for FWC. I can solve it, and that's equal to mcg cos theta. Now I come over here and I want to figure out, so that was for the cube. That's awesome. Now for the wedge, I can write down the sum of the forces in the x direction, and that's the real x, or moving horizontally across the plane, is going to be, it looks like, I'm going to draw in that coordinate system. That's this contact force, and it looks like it's the contact force times the sine of my little angle here. I'm going to draw my theta again. Everything's good. So that's FCW times the sine of the angle, and that's equal to the mass of the wedge times the acceleration. Now, this is an important point, that we don't write down the mass of the wedge plus the cube or anything like that. The sum of the forces on a free body diagram always apply only to the mass that's involved in the free body diagram, and that's the wedge here. So that's why that's just mw. Okay, now we're going after this acceleration. I know FCW because I have an expression for FWC. Newton's third law, FWC equals FCW. That's by magnitude. We've kept track of their directions using our coordinate systems, and this minus sign tells us it's pointed down here. It doesn't matter that this is a different coordinate system. We've figured out a mathematical value for just the magnitude, and I can carry that over here into this expression. So I'm going to go ahead, use this relationship, plug in mcg cos theta right up there. So I get that the mass of the wedge times the acceleration is mcg cos theta. Then I get this sine theta term, sine theta. And then that is going to be mcg cos theta sine theta. And hey, we're done, because then I solve for the acceleration as the mass of the cube over the mass of the wedge times g cos theta sine theta. I contend this makes sense because this cosine term kind of takes into account how hard the cube is pushing on the wedge. That's going to get smaller as theta gets larger. And the sine theta says how much of that push from the first part here is going to be oriented in the x direction. So that's why that gets larger. And so right there at 45 degrees, which should sort of get maximum push out in that direction. So this is good. It kind of makes sense. I like where it's going. I'm going to give us a happy face because I'm very proud of where we got to. All right, that's all we got.